Hello, Professor Zhang. The topic of our presentation is a comprehensive study of Wi-Fi 6, IEEE 802.11ax. My name is Chen Siyu, and my partner's name is Shuyu. We will introduce this topic in 7 parts: introduction, the whole economic context, system overview, channel efficiency enhancement, comparison, current challenges and future developments, and conclusion. The first part is introduction. Wi-Fi has become an essential technology in digital communications, supporting areas from home networking to city infrastructure. IEEE 802.11 is the basic standard of Wi-Fi, and since it is introduced in 1997, it has been upgraded several times. From 1999 to 2003, the early standards are based on the 2.4 GHz and 5 GHz bands. They have a maximum rate of 54 Mbps, but lack multi-user optimization. In 2009, Wi-Fi 4 utilized dual band operating modes to support 2.4G and 5G. Wi-Fi 5 in 2014 focuses on the 5G band, and the maximum link rate is 6.9 Gbps. It supports 160 Hz channels with 256 QAM modulation. And the Wi-Fi 6 in 2019 works on 2.4G and 5G dual band, supports 160 Hz bandwidth up to 9.6 Gbps rate. And the role and the importance of Wi-Fi 6. First is coping with high-density user environments. Second is improved uplink efficiency, and the third is compatibility and resource scheduling challenges. Nonetheless, Wi-Fi 6 represents a well-structured response to these challenges and lays a strong foundation for future enhancements such as Wi-Fi 7. The second part is socio-economic context. Wi-Fi 6 empowers multiple verticals through technological innovation, such as the smart home, the IoT field, and so on. For a smart home, the high-density connectivity and the low latency are the two most features. It supports 50-plus devices, smart speakers, cameras in the home online at the same time, and allocate bandwidth to different devices on demand through OFDMA technology. When it comes to the IoT field, targeted wake-up time protocol improves the endurance of sensor devices by a factor of 4. It enables IoT devices to remain dormant as long as possible, thereby realizing reduced power consumption. The chain impact and economic value. For chip companies, the self-developed chips support Wi-Fi 6 to popularize their use. In addition, for communications class operators, for example, the China Mobile has launched the whole house Wi-Fi 6 package, which will cover 60 million households by 2023 and increase ARPU by 12%. In this case, it will inevitably lead to economic development. Wi-Fi 6 devices market reached $21 billion by 2023, expected to cross $50 billion by 2028. The features of Wi-Fi 6 will lead to lower operating costs as well as increased efficiency. After deploying Wi-Fi 6, the average network O&M cost of an organization is reduced by 25%, and employee productivity is increased by 18%. The third part is system overview. Wi-Fi 6 introduces a number of innovative mechanisms at the MAC layer. The first one is the distributed coordination function, DCF. It's the earliest and most basic media access control mechanism at the MAC layer. It is a distributed competitive access mechanism based on CSMACA. The workflow is that each device listens to the channel before transmitting, waits for a random back-off time if it is idle, and then transmit the data. The ACK acknowledgement mechanism is used to ensure reliable data transmission. In addition, in Wi-Fi, the hidden node problem may occur. Node A out of range of node C, so collision of occurs at node B if both node A and C transmit. The RTS-CTS mechanism has been reduced to cope with the hidden node problem. It ensures that all nodes within the transmission range are informed about an upcoming transmission and differ potential transmission attempts. And the figure on the right side will clearly show the working method. The second part is the multi-user OFDMA. Although OFDMA is a physical layer transmission mechanism, the MAC layer is responsible for orchestrating its multi-user scheduling, resource allocation, and trigger frame coordination. The MAC layer divides the channel into resource units through dynamic scheduling, allowing concurrent transmission by multiple users. For example, the AP can allocate 242 ton RUS for video streams and 26 ton RUS for sensor data to maximize spectrum utilization. And then is the targeted wake time, the TWT. In TWT, a schedule is established between the terminal and the AP, which is composed of TWT time periods. Usually, the TWT time period negotiated between the terminal and the AP consists of one or more beacon periods. I will explain this with the help of an example. As shown in the figure, user 1 and user 2 have agreed with the AP on two TWT time periods, TWT1 and TWT2, TW1 and TW2, respectively, and the terminals user 1 and user 2 work in sleep mode by default to maintain a low power consumption. When TWT time period arrives, the AP will send a trigger frame to the terminal, which wakes up and performs data exchange with the AP. And when the data exchange is completed, the terminal returns to sleep mode. And then is the 4 working modes of TWT: sleep, receive, idle, receive, and send, and 3 working methods: individual TWT, broadcast TWT, opportunistic PS. And the features and the controllers are clearly presented in the table. And all mechanisms can be used in conjunction with OFDMA to realize the parallel wake-ups and data interactions for multiple users. Next is the BSS coloring. Wi-Fi 6 adds a color to each basic service set to help devices distinguish between their own BSS and overlapping BSS. Each BSS has a unique identifier embedded in the MAC frame header. When a device receives a frame, it compares the colors and evaluates the received signal strength. If the signal is below a certain threshold and comes from a different color, the device may ignore the transmission instead of deferring access. This mechanism allows multiple overlapping BSS to reuse the same channel more efficiently, especially in high-density deployments such as office buildings. And color allocation process may occur in same frequency band. There are two exactly the same color AP. This situation is color collision. Once the conflict means that the overlapping parts of the two BSS will be caught in the process of misreceiving and invalid decode. When a color conflict occurs, all nodes in the conflicting AP will be aware of it and will immediately report it to their own AP, which will send an action frame when it receives this message, which will notify the node of the new color and the start of the new color switch time. And that is a dynamic sensitivity control. It is a MAC layer technique induced in Wi-Fi 6 to enhance spectral used in dense networks. It allows the device to dynamically adjust its carrier sensing threshold based on the observed ISSI of neighboring transmissions. A higher CST enables more spectral reuse by ignoring weak signals, while lower CST reduces the risk of hidden terminals. MAC layer controls when and how the stations access the channel, and the physical layer defines how bits are modulated and transmitted over the air. And the first one is the OFDMA. It is one of the most key technological breakthroughs in Wi-Fi 6. OFDMA divides the entire channel spectrum into multiple smaller RUs, each containing several sub-carriers, allowing different terminal devices to send or receive data in parallel at the same time, thus realizing true multi-user concurrent communication. Wi-Fi 6 supports several kinds of RUs: 26 ton, 52 ton, 106 ton, 242 ton, up to 922 ton RUs can be divided onto the 20 MHz channel so that the access point can dynamically allocate the appropriate RU size and number according to the service requirements. OFDMA supports multi-user concurrency, reduces latency, and enhances spectrum utilization. Combined with trigger-based MAC control, FDMA can improve uplink scheduling efficiently. And next is the 124 QAM. Wi-Fi 6 introduces two new modulation and code schemes, MCS 10 and MCS 11. They correspond to modulations of 1024 QAM. The 10 bits of data transmitted per single bit, just as the figure shown. This represents a 25% increase in data transfer performance over the Wi-Fi F, with up to 252 QAM modulation. But this kind of improvement needs more ideal case, and signal strength is high enough and the noise level is low enough. It means that the SNR should be large. For this characteristic, 1024 QAM mainly used in environments with short communication distances and good link quality. And then is the MU MIMO. MIMO was introduced in 802.11n to overcome the multipass effects that arose with the standards 802.11 APG in complex radio environments. With MIMO, the signal is transmitted and received through multiple antennas, increasing the number of data streams that can be transmitted in parallel. Wi-Fi 6 adds uplink MU MIMO on top of Wi-Fi 5 downlink MU MIMO, and also improves Wi-Fi 5's maximum support of 4 multiplied 4 downlink MU MIMO to a maximum of 8.8 multiplied 8 uplink and downlink MU MIMO, which increases the downlink capacity by 2 times and the uplink capacity by 8 times compared to Wi-Fi 5. And then the last one is the guard interval. It is a short time buffer between OFDM symbols to prevent inter-symbol interference caused by multipass propagation. And it supports 3 different lengths of guard interval: 0.8 µs, 1.6 µs, and 6.2 µs. Guard interval serves to prevent the ISI, and longer guard intervals help to cope with propagation environments with large delay extensions, as longer OFDM symbols allow the length of the guard interval to be increased without sacrificing spectral efficiency, and this will also influence different symbol time, which can be adapted to diverse needs.
Hello everyone, my name is Shuyu, and I will introduce the following part about the Wi-Fi 6. First, it comes to channel efficiency enhancement. Wi-Fi 6 not only makes important optimizations in channel coding, it also achieves significant improvements in message encryption and communication security. Together, these improvements not only improve the reliability and efficiency of communications, but also dramatically reduce latency. Next, I will highlight several channel coding and modulation algorithms used in Wi-Fi 6. We will look at their individual strengths and what specific improvements they offer over previous technologies. These technologies don't work in isolation, but rather in conjunction with each other to achieve a more efficient and stable wireless communication experience. The first is the LDPC coding, also known as low density parity check, which is a linear package coding algorithm used to correct miscodes during data transmission. Its error correction capability is very high. Theoretically, it is very close to the channel limit, the maximum upper limit of channel capacity. Not only is LDPC used in Wi-Fi 6, but it is also used in other advanced communication technologies such as 5G. It can be used to control the channel, and also according to the literature, LDPC provides security in an information theoretic sense. When evaluating the role of channel coding for information security, we usually use the concepts of strong secrecy or weak secrecy. The former one means that the correlation between the information of the sender and the receiver is so low that it can be almost ignored. Weak confidentiality means that the average mutual information per bit tends to be close to zero. Next, let's take a look at a very important mechanism optimization in Wi-Fi 6, the OBSS-PD algorithm. Besides Wi-Fi 6, for example, in early standards such as Wi-Fi 5, systems relied on a mechanism called clear channel assessment. It determines whether a packet can be sent by identifying the strength of interference in the channel. CCA includes two mean threshold determination methods. The first one is preamble detection CCA. It identifies the boundaries of a message and estimates the signal strength. The standard threshold set in the protocol is -82 dBm. The second one is energy detection CCA, and its threshold is -62 dBm. However, in high-density network environments, the traditional CCA strategy has an obvious drawback. If the client uses too much transmit power, it will instead cause additional interference. To solve this problem, Wi-Fi 6 introduced a new technology called spatial reuse. The goal of this technology is to reduce co-channel interference and improve the overall efficiency without sacrificing communication quality. Based on the idea of spatial reuse, Wi-Fi 6 proposes the OBSS-PD, which is Overlapping Basic Service Set Prediction Detection mechanism. The core idea of OBSS-PD can be summarized as follows. When a strong energy OBSS signal is detected, it means that there is already a strong interference source around. In this case, the device raises the OBSS-PD threshold and reduces its own transmit power to avoid interfering with each other. On the contrary, if a weakly energized OBSS signal is detected, it means that there is less interference. In this case, the device will lower the OBSS-PD threshold and increase its transmit power to enhance its communication capability. Finally, let's return to the topic of the channel access mechanisms. In Wi-Fi 6, a very key technology, orthogonal frequency division multiple access, OFDMA, has been introduced, which brings a huge enhancement to the wireless communication system. These two diagrams show the channel access mechanism for Wi-Fi 5 and Wi-Fi 6 respectively. The addition of OFDMA makes Wi-Fi more suitable for those scenarios with higher requirements for higher reliability and low latency, such as high-definition online gaming, industrial IoT, and so on. OFDMA allows multiple users to share channel resources at the same time, unlike in the past when only one device was served at a time. This greatly improves the efficiency of spectrum utilization. The next part about Wi-Fi 6 to describe is the comparison with different technologies. We have talked a lot about Wi-Fi 6 technical advantages and the mechanism improvements. So next, let's look at how it compares with other mainstream wireless communication technologies. In this section, we briefly compare Wi-Fi 6 with Wi-Fi 5 and 5G. Let's start with the first comparison, Wi-Fi 6 versus Wi-Fi 5. As the predecessor of Wi-Fi 6, Wi-Fi 5 played an irreplaceable role in the development of wireless communications, especially in the 2010s. Wi-Fi 5 achieved a number of technological breakthroughs at that time and breaking the 1 gigabit per second transmission rate bottleneck for the first time, so it is also known as gigabit Wi-Fi. Wi-Fi 6 further evolves on this foundation, achieving higher efficiency, greater reliability, lower energy consumption, and a theoretical maximum rate of nearly 10 gigabit per second. Wi-Fi 6 introduced a series of brand new standards also. According to a paper published in 2023, the core differences between Wi-Fi 6 and 5 can be summarized in 5 aspects: AP capacity, AP spatial, frequency range, maximum data rate, and multi-user MIMO technology. The development of OFDMA is like OFDM, reducing the interference in channel effectively. However, OFDMA can connect multiple clients simultaneously by distributing spectrum resources to different users. It can obviously increase the number of users and short packets transmitted, while decreasing the sacrifice of the performance of communication, such as the transmission error and the data delay. Besides, Wi-Fi 6 can be faster in performance because it has more spatial streams, representing higher maximum potential throughput. For Wi-Fi 5, it can only support 4 to 8 spatial streams, while Wi-Fi 6 can reach 8 streams already. This leads to the final improvement in the transmission performance. The third difference is the frequency bands difference. Compared with Wi-Fi 5, which can only use the 5 GHz frequency band, Wi-Fi 6 can utilize both the 2.4 GHz and 5 GHz, also resulting in higher throughput. Summarizing all three differences above, including the access points and frequency bands, it will certainly result in an improvement of the data rate. According to the literature, the ideal data rate for Wi-Fi 5 is about 6.9 gigabit per second, while the case for Wi-Fi 6 is around 9.6. For both ideal cases, Wi-Fi 6 is more likely to achieve this target. And the final difference is shown in multi-user MIMO. Compared with traditional MIMO technology, multi-user MIMO can provide higher speed, higher reliability, and higher communication. Based on this, Wi-Fi 5 only supports downlink multi-user MIMO, while Wi-Fi 6 can support both the uplink and downlink communications. Next, let's look at another comparison, Wi-Fi 6 versus 5G, the fifth generation of wireless communication technology. This technology is recognizable in the daily lives of the general public, and it has become an irreplaceable part of society's communication system with a wider range of applications. 5G is more suitable for large range and wide coverage communication needs, such as city-level communication and transportation systems. Wi-Fi 6 is better suited for indoor high-density scenarios, such as office buildings, home networks, classrooms, or shopping malls. We can compare the two technologies in three ways: technical characteristics, spectrum utilization, and economic cost. First, it comes to the technical characteristics. In terms of peak rate, the theoretical data rate of Wi-Fi 6 can reach 10 gigabit per second, which is much higher than the 2 gigabit per second of 5G. However, in terms of multi-user MIMO technology, 5G is more capable of supporting much more configurations than Wi-Fi 6, which means that 5G is more suitable for wide area network environments. In terms of coverage, 5G has a clear advantage, especially in small configurations that can cover 100 to 300 meters, while Wi-Fi 6 typical coverage is within 15 meters, mainly for indoor scenarios. The second part is the spectrum utilization. In terms of frequency band types, 5G covers a wide range of frequencies, including low, medium, and high bands, while Wi-Fi 6 mainly concentrates in the low and medium frequency ranges and is more suitable for indoor and high-density scenarios. Overall, Wi-Fi 6 focuses more on flexible, low-cost, local deployments, while 5G favors wide area coverage and operational-grade network control. Finally, it comes to the economic cost. In terms of business model, 5G belongs to the traditional pay-per-use model, where users need to pay for data services on a monthly basis. Wi-Fi 6, on the other hand, is mostly provided free of charge as an amenity or local network service, especially in private scenarios such as shopping malls and campuses. Overall, Wi-Fi 6 is more economical and better suited for local internal communications, but 5G emphasizes wide coverage and high performance, but at a relatively higher cost. And finally, it comes to the current challenges and future development of Wi-Fi 6. In summary, while Wi-Fi 6 represents a major step forward, it still faces challenges in meeting the ever-increasing demands for speed, efficiency, and capacity. The ongoing development of Wi-Fi 7 provides a promising direction, and by comparing the two, we can better understand the future of the wireless communication. First, selecting the optimal modulation and coding schemes, MCS, becomes more complex due to a larger set of options and influencing parameters. This introduces a multi-criteria optimization challenge, making it essential to adopt effective MCS adoption strategies, particularly in large-scale Wi-Fi deployments. And then, to support QoS in Wi-Fi 6 networks, efficient resource assignment through OFDMA is essential. While centralized controllers can assist in coordinating access points, achieving effective slice isolation across multiple access points remains challenging, and ensuring QoS guarantees continues to be a critical issue requiring further enhancement. Besides, predicting and managing multi-vendor deployments remains challenging due to proprietary algorithms used by different manufacturers. This makes it difficult to control key processes such as scheduling and MCS selection. Additionally, the increasing complexity and cost of large-scale deployments cannot be overlooked. Therefore, Wi-Fi 6, the task group started in May 2019, which is planned to be finished by 2024. The development of Wi-Fi 7 is targeting reduced latency, enhanced spectrum efficiency, unprecedented data rates, and so on. According to the development history of Wi-Fi technology, some visible changes can be summarized. For example, the max data subcarrier modulation may be changed from 1024 QAM to 4096 QAM. More importantly, the nominal data rate may be expected to 40 gigabit per second in ideal case. The trends of Wi-Fi technology can be mainly concluded into parts. First, it's certain to be combined with advanced wireless technologies and standards such as 6G, leading to greater increase in the spectrum utilization, latency reduction, throughput enhancement, and other parameters. Besides, it will be involved with more AI-driven networks. This can help with the management of the network and improve the efficiency of connectivity. Moreover, it will be applied into more actual scenarios and applications. More and more areas have the potential to realize automation and intelligence. The application of Wi-Fi technology may break through some current technical limitations. In conclusion, we have provided a comprehensive overview about Wi-Fi 6, covering its system architecture, technical enhancements, socio-economic impact, and comparison with other wireless technologies. Through innovations in physical and MAC layers, Wi-Fi 6 significantly improves reliability, efficiency, and latency performance over its predecessors. Furthermore, its practical applications and role in addressing real-world deployment challenges highlight its importance in modern wireless communication. With a strong foundation in technical design and future potential, Wi-Fi 6 is poised to drive continued innovation and is well worth further study and development. That's the end of our presentation. Thank you for listening.